Hello everyone, and welcome back to another video of me talking to a screen explaining chemistry concepts I already know to a non-existing audience. In today's episode, we will be generalizing our results from Faraday's first and second laws experiments that you did last week, and we're going to use whatever we're going to generalize as well as some other stoichiometric ratios and formulas that you've learned in the past to calculate different quantities relating to an electrolytic cell. So we're looking at 6.6 and 6.7 in the dot point in the course outline. So be a lot of algebra today. Now we're going to be celebrating the work of Michael Faraday, who is my favorite scientist, and every year when I teach this topic I need to talk about Michael Faraday because I think these laws in particular and Faraday's works in general really emphasizes the essence of science, which is observations from experimentations. And sometimes when we learn science in the classroom, we tend to forget that this was done. Like a lot of these laws and principles and theories were developed based on humans' observations and experimentations. And nobody exemplified that more than Michael Faraday because he received very little formal education at a time when science was generally a field of the upper class. You need to have a lot of money to be able to go to university and then to be able to afford equipment to do experimentation. And Faraday was really poor. He was from the lower class, and he managed to become the scientist that he became because of experimentation. So I could go on for hours on Michael Faraday, but anyway, my favorite scientist. And I'm pretty sure the physics people have heard of his name before. So we're focusing specifically on Faraday's laws for electrolysis, but in chemistry, I think this is the only time that he appeared in electrochemical chemistry. So we're just going to call it Faraday's laws. I hope it's not too confusing for you. Some basic concepts that you should have seen when you did the experiment and if you read the introduction to the experiment. The first one is the concept of charge, which is current times time for current in amps and time in seconds. Somebody made a comment on this in their report, but the unit for charge is coulombs or C. Some people are really into triangles, so you can do a triangle for this if you want. So Q is I times T, and I really hope you don't have to at year 12 level, but anyway, Q equal to IT. This is a recap. We looked at this in energy calculation, so thermodynamics. So E is VIT. So if you really like triangle, that's another one you can make. Now, because you can't calculate Q as IT, so another way of writing this triangle, if you just replace IT for Q, is you can have E equal to V times Q. So this is a connection between charge and energy. All right. So this is the experiment that we did. So Faraday's first law, which was the first experiment that you should have done, the aim is to determine the relationship between the mass of metal at the cathode and the quantity of charge. So if you change the amount of charge supplied to the cell, would that change the amount of mass that is plated at the cathode? So that was the purpose or the aim of the first experiment. And this is just an example of the result. So your result may be a little bit different from this. But essentially what we need to do is we need to keep everything constant except for the current. So the independent variable for this experiment is actually the current, because you're actually keeping the time the same. So by varying the current, because Q is I times T, by varying the current, you are varying the charge supply to the experiment, and you are measuring the mass deposited at the cathode. So this is your, the independent variable really is the current, but you're varying the charge to determine the mass of metal deposited at the cathode. So if you plot a graph, and I was a little bit concerned when I read some of your report because some of you didn't plot this, but essentially the charge should be the horizontal axis. The horizontal axis normally is reserved for the independent variable, or the things that you actually vary, and the vertical axis is the mass of zinc. So the mass of zinc in this case is the metal being deposited at the cathode. the mass of zinc is going to depend on the charge supply. And if the aim of the experiment is to determine the relationship between these two variables, you really want to make one variable the horizontal axis and one the vertical axis. I don't know. I thought that was obvious. Anyway, so if you plot that, you're going to get this, or something like this. So it's a perfect linear relationship. Obviously, in an actual experiment, you can run a cell at 0 charge and you really should have 0 mass. So you could connect the last dot and you're going to get a perfect linear relationship that way. So from there, you should be able to conclude or derive Faraday's first law. Faraday's first law is really easy to remember. It's the second law that's... Okay, so the first law is the mass of any substance deposited, evolved, or dissolved. So we're going to talk about gas, product, and metal ions later. But the deposited one is the one that we look at in the experiment. The mass of any substance deposited, evolved, or dissolved at an electrode in an electrochemical process is directly proportional to the amount of electricity passed through the cell. Just to remind everyone that direct proportionality refers to a perfect linear relationship. So it's not just that if one increases, the other increases, they increase in a linear relationship. Okay, so if you increase charge, the mass should increase at the same rate, I guess. Now, some people wonder whether you actually have to memorize Faraday's first laws and second law, and in the majority of cases, you don't have to. You just need to know a formula that I will show you in a little bit. But there was an exam a few years ago when the question actually asked the students to design an experiment to test for Faraday's laws, plural, and many students didn't even remember that there were 2 laws in the first place. That question was a mess. We'll talk about that question later, maybe, if we have the time. So this is the first law. If you want to test for this law, you want to vary the charge and measure the mass of the same metal being deposited at the cathode. All right, Faraday's second law is a little bit harder to put in words, but the aim here is you want to know whether anything will change if you change the identity of the metal. So if you go from copper to aluminium to zinc to silver, so if you have different types of metals being deposited at the cathode, would that affect the amount of metals that you will get? So basically, if you want to vary the metal that is deposited at the cathode, you would need to vary the identity of the electrolyte. So I'm just going to add an extra column here. So the metal deposited would be the metal version of the metal ion here. So if the metal ion is silver ion, the metal deposited is silver, copper, iron, and aluminium in these cases. Okay. And then we're going to measure the mass. So obviously there is a difference in the mass of metals deposited. Silver, you get a little bit more than copper, a little bit more than iron, a little bit more than aluminium. Even though everything else is kept constant, the initial mass of the cathode is constant, the charge supply is constant. Another thing that we would do for this analysis is we're going to convert mass to number of mole of metal. And the reason why we do this is because the mass of a metal is dependent on 2 things. It's dependent on the number of mole of the metal and also the molar mass. But the molar masses of these metals, of these elements, are different. Silver is a lot heavier than copper already, so it's going to affect the mass of metal deposited. So you kind of want to remove the effect of the molar mass on your experimental result, and that's why you convert the mass of the metal to the number of mole. So you have a comparison with the number of mole here, and then some people ask me how to do this, and essentially the charge required to deposit 1 mole, if you just think about ratio, you're trying to find Q for 1 mole, and the previous 2 columns already give you Q 720 per whatever mole of metal you get here. So you should be able to just use ratio and work out this without needing a formula. So you can see that the charge required to deposit 1 mole of the metal also vary depending on the identity of the metals. So something very interesting is happening here. We did ask you to plot a graph. Again, I think a lot of people struggle with understanding that when you plot a graph, you really need to put the 2 variables in the horizontal axis and the vertical axis Otherwise, you can't really analyze the graph, and anything that you get from the analysis is not going to be considered valid. So the charge is the horizontal axis here, and the number of mole of metal is the vertical axis, because once again, the amount of metal deposited would depend on the charge that you supply. You can't really see the copper one here because it overlaps with the Fe. So Fe and copper are on the same line. I'm going to label it copper and Fe because it's actually the metal deposited, even though the key said copper ions and iron. So aluminium metal is here, and this is silver. Okay. So the question that we want to answer is, why is there variation in the number of mole of metal deposited at the cathode even though you're supplying the same charge? So for example, if I supply 50,000 coulombs, you have a lot more silver being produced than you would copper and Fe, and then you produce the same amount of copper and iron in terms of number of mole anyway. So why are these two the same? And why is aluminium less than everything else? So that's the question that we want to answer. And the key to that question, I think, has to do with the half equations that occur at the cathode. So this is the equation for copper and silver. Let me just get all of them out. So the variation here is actually the mole ratio between the number of mole of metal and the number of mole of electrons. Because when you supply the same amount of charge, essentially you're supplying the same amount of electrons to the cell. So same n of electrons. But because the mole ratio between the amount of electrons and the amount of the metal varies depending on the metal, you would get different number of mole of metal being produced. So in the case of silver, it's a 1-to-1 mole ratio. So if I supply 1 mole of electrons, I get 1 mole of silver. However, in the case of copper, if you supply 1 mole of electrons, you only have half a mole of copper. So there's an issue there. No, it's not an issue, but you just get less number of mole of copper. Similarly for Fe, if you supply 1 mole of electrons, you get half a mole of iron. And this is why the number of mole of metals for copper and iron are equal to each other according to this graph. And lastly, if you supply 1 mole of electrons, you will get 1 mole aluminium. So if I just assume that the number of mole of electron is 1, I don't think it was 1 in the experiment. It was a little bit less than that, but the ratio shouldn't change. If you supply 1 mole of electron, you will get 1 mole of silver, half a mole of copper, half a mole of iron, and a third a mole of aluminium. Now again, an actual experimental result is not going to perfectly reflect this relationship, but if you repeat the experiment multiple times to improve the accuracy of the average value, you should get something very close to this relationship. I think it actually looks like this is a third. So what we're supposed to have is that being a third. Actually, no, this one's pretty good. This is a half, and that's 1. In terms of it's not actually a third, but in terms of ratio between the two. Because I think that looks like, so if that's 1, that's a half, and that's a third, ratio-wise. Another thing that you should be able to do from this graph is you can estimate the actual amount of charge that is equivalent to 1 mole of electrons. So if I look at this, so if you plate 1 mole of electrons, if you plate 1 mole of silver, that is equivalent to using 1 mole of electrons, because according to the half equation, the mole ratio between the number of mole of silver and the number of mole of electrons is 1-to-1. So if the number of mole of silver is 1 mole, that means that the number of mole of electron is also 1 mole. And if you I think you can do the actual experiment, but this value, so 1 mole of silver, in order to plate 1 mole of silver, you need to supply 96,500 coulombs. So from the experimental data, I mean, you could also try to find the equation of this line and then just sub in y with the 1 and so for x. But from experimental data, you can work out that In order to supply 1 mole of electrons, you would need 96,500 coulombs of charge. 96,500 coulombs of charge. Okay, so that's the second thing that you can get out of this. The first one is the relationship between the number of mole of electrons and the number of mole of product, and how that depends on the mole ratio between the two. And the second one is this. I'm going to give you the actual wording of Faraday's second law, which is a little bit ridiculous, and then we're going to go back to this number in a little bit. So this is second law. I have never seen, okay, I haven't seen yet, but it might happen this year. I haven't seen an exam when you actually have to state second law or any of the Faraday's laws, but you do have to design an experiment that would test for it. So you need to know what it is, even if you can't put it in words nicely. And this is not nice whatsoever, but this is a second law. For 1 mole of a substance to be deposited, evolved, or dissolved at an electrode, the passage of 1, 2, 3, or another whole number of moles of electron is required. Like, who came up with this? I don't think Faraday actually wrote this, but it's just trying to say that there is a ratio between the electrons and the amount of metal. But anyway, we'll talk about the calculations based on the second law. So I'm just going to go back to the 96,500 coulombs. A charge of 96,500 coulombs is equivalent, probably should use proper English, is equivalent to 1 mole of electrons flowing through the circuit. 96,500 coulombs is also known as 1 Faraday, and the symbol for Faraday's F. So 1F is 96,500 coulombs. 2F will be double that, obviously. And another way to write it is if I just write, so 96,500 is equivalent to 1 mole. So this gives you a ratio between the charge and the number of mole of electrons. Now, if you rearrange this equation, actually I wrote it here. Yeah, if you rearrange this equation, you should have Q would equal to number of mole of electron times Faraday. So if I just rewrite that, so Q over N of electrons equal to F over 1 mole, because F is 96,500 coulombs. Then if you just move F to the other side, or cross multiply, or whatever you want to call it, this is the equation you're going to get. Q equal to N electrons times F, or Q equals to N electrons times 96,500 coulombs. So that will allow you to calculate charge based on the number of mole of electrons. If you're really into triangle, this is the triangle that you can make. So Q is N electrons and F. So Q is charge, N electron obviously is mole, and F is charge per mole, or coulombs per mole. That will be the unit for F. Okay, this is given to you in your data book, page 5. So that's Q equal to IT, which is the first one that I showed you at the start of the video. This is another representation of Faraday's, of the calculation that we just did. The thing that I don't like about the data book sometimes is, maybe it's not the data book, maybe it's students' inability to transpose, but sometimes you look at this and people actually don't know what to do with it. So there's that. They also tell you what F is with unit, so just keep in mind you have it on page 5. And I just want to tie everything together and talks about the difference between charge supplied and charge received. Because right now we have 2 different formulas for calculating charge. So if you look at an electroplating experiment, this is your power supply, and your power is going to be supplied to the cell via current and time. So you set, and voltage as well, but you don't really need to worry about voltage. So you can set the current, and then you can set the time, and obviously you set the voltage. So if you know the current and the time, you basically can calculate the charge that you're supplying to the cell. So when you use the formula Q equal to IT, or if you really like triangles, Q is I times T here, you are calculating the input charge or the charge that is supplied to the cell, because it's a measure via current and time. When you use Q equal to number of mole of electrons times F, which is the second way to calculate charge, this is when you calculate the charge that is received by the cell, because the charge that is received by the cell and then eventually turns into the product that is plated onto the cathode, that is going to be reflected by the number of mole of electrons that actually flow between the cathode and the anode. Because in reality, the charge supply is always going to be greater than charge received. So if you supply, I don't know, 70,000 coulombs, you're probably not going to receive all of it. So in reality, this Q is supposed to be bigger than that Q. A lot of the times, if the question didn't mention anything, then you would assume that they equal to each other. But then there will be types of questions when you have to calculate percentage efficiency, and that's when you have to realize the fact that the charge received should always be lower. Let me just write it out, because sometimes people are confused with inequality sign. So charge received is lower than charge supply. And this is obvious because you're going to lose some energy in the form of heat and sound and whatnot due to energy loss in the wire. We're going to talk about specific examples relating to this when we look at the questions later, but this is just to give you a distinction between the two values, the two formulas for calculating charge. That's it for this video.